Among the main culprits in the cosmic dilemma are dark matter and dark energy. Although neither dark matter nor dark energy have been explicitly seen or demonstrated to exist, current models indicate that they collectively account for over 95% of the universe. They might not even exist or might have characteristics that are still unknown to us. A possibility under discussion is that the properties of these dark components could have changed throughout time. While principles of spacetime curvature mostly drawn from Einstein have been repeatedly validated, gravity, which should produce attraction through mass or spacetime curvature, has not been proven satisfactorily. We cannot completely rule out the idea that gravitational attraction is caused by some other phenomenon, or that there are qualities to gravity that are different from what we have traditionally believed. As a result of their stability, some features in cosmology and astronomy have been recognized as enormous constants over time and are taken for granted. Based on calculations, small changes in these constants may shed light on anomalies and reveal new information about the universe. It is also possible that in the absence of dark energy, our interpretations of light shifts have been inaccurate, resulting in inaccurate estimates of galaxy ages and distances. It's possible that we misread the cosmic microwave background radiation, or that our theories about the early conditions of the universe were incorrect. It's even possible that the hypothesis of primordial cosmic detonation is challenged by the possibility that the cosmos does not originate from a single spot. Even with the progress of technology, small errors in the JWST or other observational instruments cannot be completely ruled out. Errors in instrumentation data processing or interpretation are always conceivable, and scientists and researchers are aware of this. The ongoing evaluation of cosmological hypotheses brings to light an essential component of scientific progress: the capacity to modify and improve our knowledge in the face of fresh data. The discoveries made by the JWST signify not only a technological advance but also a pivotal point in our investigation into the secrets of the cosmos. It is critical to understand the larger context and ramifications of such scientific advancements in cosmology. As we wrestle with these findings, the necessity to reconcile observations with theoretical models frequently drives the process of hypothesis refinement. Finding unexpected inconsistencies or anomalies in accepted ideas might be disconcerting, but it also offers a great chance for scientific advancement. In cosmology, theoretical models are built to offer a logical framework for comprehending the beginnings, composition, and development of the cosmos. However, these models need to be tested and, if needed, updated to account for new information as it becomes available. The ideas of dark matter and dark energy, which are essential to modern cosmological models, represent one important topic of study. It was suggested that discrepancies between observed galaxy spins and the mass expected by visible matter alone could be explained by dark matter, an unseen kind of substance that neither emits nor absorbs light. To further explain the apparent faster expansion of the universe, dark energy was included. Even with their crucial positions in existing models, dark energy and dark matter are still mysterious. Since investigations on Earth have not been effective in directly identifying dark matter, scientists are now investigating other theories and possibilities. Complicating the problem of comprehending dark matter and dark energy is the enormous scope of cosmological research. While indirect evidence for these components can be found in observations of far-off galaxies, cosmic microwave background radiation, and other cosmic events, their composition is yet unknown. Because of this uncertainty, scientists have been thinking about a variety of theories, from new ideas to adjustments to pre-existing beliefs. For instance, some ideas propose that dark energy might be an indication of a new basic force, or that dark matter might include more exotic particles than previously thought. The study of cosmic inflation, which postulates that the universe experienced rapid expansion in its early stages, giving rise to the large-scale structure we see today, is another fascinating facet of cosmological exploration. Although the universe's uniformity and isotropy have been satisfactorily described by inflationary theory, the theory also begs the question of what the inflationary phase was like. Revisions in our understanding of the early history of the universe may be necessary in response to later data that contradict established models of inflation. Moreover, one of the main forces behind cosmic exploration is still the search for extraterrestrial life. The finding of exoplanets, or planets around stars outside of our solar system, has created fresh opportunities to study the circumstances that support life. Researchers may now examine the atmospheres of these exoplanets to look for possible biomarker signals, thanks to advancements in telescope technology such as the James Webb Space Telescope (JWST). Our knowledge of the universe and our place in it is significantly affected by the prospect of life beyond Earth. Quantum gravity and string theory are two well-known theoretical physics attempts to bring our knowledge of the fundamental forces together. According to string theory, one-dimensional strings vibrating at different frequencies rather than point-like particles make up the fundamental components of the cosmos. The goal of this theory is to bring quantum mechanics, which controls particle behavior at the smallest scales, and general relativity, which describes gravity, into harmony. Though string theory is extremely theoretical and technically hard, it has sparked creative ways to investigate the properties of matter and spacetime. In contrast, the goal of quantum gravity is to provide a framework that integrates the ideas of general relativity and quantum mechanics. Loop quantum gravity, which suggests that spacetime itself possesses a distinct granular structure at the tiniest scales, is one of the leading contenders in this subject. The goal of this method is to reconcile the stochastic nature of quantum physics with the smooth spacetime of general relativity. In contemporary cosmology, the interplay between theory and observation emphasizes the dynamic character of scientific investigation. We can more precisely test and improve theoretical models as our observational tools improve. Gravitational wave astronomy, for example, has made it possible to focus on anomalies such as neutron-star collisions and black hole mergers, providing fresh insights into the fundamental properties of matter and gravity. These discoveries have raised fresh questions about the nature of spacetime in addition to confirming general relativity's predictions. Parallel to this, the study of astrobiology looks into the possibility of extraterrestrial life by modeling harsh environments on planets other than Earth. The study of extremophiles, organisms that survive in hostile conditions such as high heat pressure or radiation, offers insights about the kinds of settings in which life might persist in other places. This multidisciplinary method improves our comprehension of the possible habitats and structures of extraterrestrial life by fusing planetary science and biology. Carlos Straight, a teacher, claims that he has dedicated his career to promoting a specific universe theory. Now the theory is being examined closely in light of the developments made by the JWST. He welcomes the task since he thinks that it is through close examination that science progresses and advances. In essence, the JWST is challenging certain long-held cosmological beliefs that have been accepted as true for a century. It has come to light through another really fine photograph that our faults in space science are real. The telescope, which was once intended to reveal the universe's first stars, offers a startling new viewpoint that may result in a totally different understanding of science. While it has long been known that there were issues with earlier theories, many scientists are relieved by these new findings rather than alarmed. Even the differences in the rates at which the cosmos is expanding should have worried scientists a long time ago, but many adhere to antiquated notions rather than appropriately comprehending these warnings. The cosmos' oldest light, known as the cosmic microwave background radiation (CMB), was produced some 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine to form stable hydrogen molecules. The universe became transparent to light during this shift, which is referred to as reionization. American scientists Arno Penzias and Robert Wilson discovered the CMB for the first time in 1964 while developing new antenna technology. At first, the continuous roar they heard coming from every direction in the sky was thought to be solid proof of the Big Bang theory. For this finding, which laid the groundwork for future astronomical discoveries, Penzias and Wilson were given the Nobel Prize. It is believed that the CMB offers a glimpse into the early cosmos with minute temperature variations, providing important information about circumstances immediately following the Big Bang. Scientists use the CMB as a trustworthy fingerprint to calculate important properties of the material universe, such as the rate of expansion. When Edwin Hubble noticed that distant galaxies are moving away from us and that their speed is related to their distance, a relationship now known as the Hubble law or Hubble constant, he had already made similar observations in the late 1920s. Hubble's measurements were fundamental even though they were not as exact. Astronomers recalculated the expansion rate after the discovery of the CMB and found it to be much lower than Hubble's original estimate. A more precise estimate was obtained through subsequent recalculations with Type Ia supernovae as standard candles, although inaccuracies remained. Since the 1990s, the disparity in expansion rate approximations has been recognized. There have been speculative claims regarding possible problems with the CMB data estimating methods or the idea of universal expansion. The Hubble tension, also referred to as the S8 tension, is a discrepancy that raises the possibility that our comprehension of the cosmos is essentially incomplete. The JWST has produced astounding data since it started operating, which may shed light on this problem. Scientific beliefs are being challenged by galaxies so old and developed that their formation should theoretically precede the Big Bang. The rate at which the universe is expanding and the theory behind its origins are under investigation, posing what is regarded as the greatest issue facing modern astronomy. The photos from the JWST show a cosmos that is essentially different from previous models. The S8 tension was the first red flag, and now scientists stuck with antiquated theories are in a difficult situation. Many scientists are worried and perplexed by the possibility that our knowledge of the universe